All right. All right. Okay, get where you can see. Is that good? Can you see everything? If I do that, are you fine? Yes, see, okay. Okay, get where you can see. Why don't you ladies come on kind of in here a little bit so we can see a little better. Come on up and turn those desks around. Get comfortable up here. We're going to look at something, another property of matrices called determinants. This is a determinant, it turns out, is just going to be a number. It's just a number associated with any square matrix. And what do you suppose we mean by a square matrix? What do you think, Kim? Yeah, okay, good. So like 2 by 2, 3 by 3, 10 by 10, same number of rows as columns. So as long as it's a square matrix, for every square matrix, we can calculate this number called the determinant. And it's going to seem a little wacky how we do this, but it has a lot of important meanings. We'll look at just a couple, today we'll look at maybe just a couple quick applications of this, but there are a lot more. Okay, these are kind of mathematical applications, but there are some non-mathematical applications as well. Okay, so first of all, the determinant, if the determinant that we're taking is for matrix A, and notice that we use capital letters for matrices. That's kind of normal. You can write a matrix in different books and different places, different websites. We'll write a matrix in different ways, but a lot of times we'll write it this way. We'll either say in brackets like that. Sometimes you'll see that as that denotes matrix A, or maybe it's just a capital A. But you see it, different ways. Typically, though, it involves a capital letter. Okay, a determinant, we either write with a lowercase det, and that's the way our calculators do it. When you go to, and I'll show you on the calculator here in a little bit how to do this. When you go to the matrix screen in the math menu, it'll say det, which means determinant. The more common kind of old school way is this way. We just put the matrix inside what looks to be absolute value bars. Only when we're talking about matrices, that doesn't mean absolute value bars. Let me get this calculator going while I'm thinking of it. Okay. So the determinant of a 2 by 2 is, I'll get this out of here in a second. I'm going to show you how to calculate a determinant by hand for a 2 by 2 and even for a 3 by 3. And then you can kind of see you can sort of see what the process is for even bigger matrices. But like everything else we're doing with matrices this year, really, I'm going to show you, give you a little glimpse of how to do this stuff by hand, but we'll do it on our calculators because that's just how you deal with matrices now. It's so much quicker and easier than it used to be. Okay, so determinant of a 2 by 2. So if we're taking the determinant of this matrix, and what this kind of a clumsy way it's written up here, what that means is it's 2 by 2. The first row has entries A and then B. And then the second row has entries C and D. This probably should be spaced out a little bit more, but you get the idea. Okay, to calculate the determinant, then that looks a little better. So this means determinant, because it's got the straight bars of that 2 by 2 matrix. All you do is you take the product of the descending diagonals minus the product of the ascending diagonals. So descending means going down, ascending means going up, right? So we're going to say A times D, that product, minus C times B. Okay? And whatever number you get, that's the determinant. So pretty simple for a 2 by 2. What's our determinant going to be for this 2 by 2 matrix then? What minus what? 7 minus 8. That's it. -1. That's the answer. That's the number. Okay? Piece of cake for 2 by 2. Really not a big deal. So this one would be, real quick, 21 minus 4. Good. So we get 17. Okay, what about a 3? Oh, that's kind of hard to see. What about a 3 by 3? For a 3x3, it gets a little bit trickier, and this is kind of a common thing we do with matrices. For a 3x3, we're going to have 3 descending diagonals and 3 ascending diagonals. And to build those, it's kind of like on a video game. You guys ever play, like, there was kind of a resurgence of some of the old school video games. Have you ever played Asteroids before? You know, in Asteroids is a great model for a lot of things in math and physics. It's because in Asteroids, if this is the screen, and this is, kind of takes me back to the day a little bit. Asteroids was the latest and greatest when I was a kid. So with Asteroids, if a ship goes off the screen in this direction, where does it appear? Yeah, it appears right there on the other side going that way, right? Remember that? That is, by the way, in physics, that's what we call a multiply connected universe. And it means that when you go off one side, you come back in the other side. There's a chance our universe is really that way. There's a chance. It's getting slimmer and slimmer as we learn more and more about the universe, but there's a chance that if you go forever in that direction, you'll find yourself coming back on yourself from the other direction. That really could happen. Oh, my goodness. Yeah, okay, good. So anyway, this is sort of like an asteroids game. What you got to do is when we're calculating this diagonal right here, we're just going to come back onto the screen down there, if that makes sense. Okay. The easiest way to think about that, though, is just to take the first 2 columns and just repeat them at the end and keep going. So I would take this first column right here and rewrite it, and the second column and rewrite it. And then when I make my descending diagonals, I've got a diagonal there, plus that diagonal, plus that diagonal. I can see them all as straight lines. Okay. I'll show that to you a little more clearly on here. So if we repeat those, then we're going to get, there's one product. All 3 of those. 2 times 0 times 6 plus the next diagonal, negative 3 times 1 plus 4 times 2 times negative, 4 times negative 2 times 2. Okay, we take the sum of all the descending diagonals minus the sum of all of the ascending diagonals. So the quantity in parentheses, 1 times 0 times 4 plus 2 times 3 times 2. You see the pattern. Matrices are all about patterns. Once you get the pattern, just follow it. Plus 6 times negative 2 times negative 3. So there's the sum of the descending diagonals. We get the ascending minus the descending. It's just a matter of crunching those numbers. And that's no big deal. If we crunch the numbers, we end up getting, evidently, an answer of negative 73. You can see that starts to get a little time consuming, though, doesn't it? Now, when you get up to a 4x4, it even gets more complicated. Then it becomes pretty bizarre. But we won't even mess with that. We won't even mess with that in here. Suffice it to say that we know how to do it, right? And I won't even, we could do this, right? Remember, all we would do is just recopy, repeat the first 2 columns, make our 3 descending diagonals, add them up, make our 3 ascending diagonals, add them up, and subtract the 2. Yes?
So can we do this on the calculator?
Yes, you can. That's what I want to show you how to do, is how would you do this on a calculator? Okay, so let's take this example, and let's use our calculators instead. Okay, so if I pull up the calculator, I bet you can even guess how to do this. If you just guessed how you think it would work based on what you did on the calculators previously, I bet you're right. What do you think we do? Can you see? That's really hard to see, isn't it?
Would we multiply?
No. What do you suppose we do, though, before we do anything? Cammy, what do you think?
Just put those numbers into matrix.
Okay, so we're going to build a matrix. We're going to build that matrix first of all, right? So we'll go to second matrix. We have to scoot over to edit, don't we? So scoot over to edit, and we'll make matrix A be that matrix. Now, what do the dimensions need to be? 3 by 3. Okay, and then we'll just put them in. 4, enter, 3, enter, 1, enter, 5, enter. get matrix A in there, let's quit. We want to get out of the edit screen. So we built that matrix, okay? Now we'll go back to the matrix screen, and we're going to scoot over to the math menu. Now the math menu is where we can do all kinds of operations on matrices. Some of these are going to look a little strange, like that transform, and some of these are going to look a little bizarre. But determinant is the one that we want, isn't it? Right? So we'll go up to, actually it's the first option, so we'll just hit enter. And then it's saying the determinant of, and then in parentheses, you're going to enclose whatever matrix it is that you want to take the determinant of. So how do we get to the A?
Second matrix.
Second matrix. Enter. Okay. Close the parentheses, and look what it does. There's the answer. Okay. Gives us the determinant. How easy is that? And what's nice about this is, I could make the matrix as big as I want to. It doesn't matter. The calculator can manage even a really big matrix very quickly, whereas it would take you by hand quite a while to calculate a big determinant.
But I can't do it, right, that once you do a big matrix, it doesn't do 100 by 100.
The 100 by 100 would probably break it. Yeah, I mean, not break it literally, but it's not going to be able to do that
Or it
algorithm.
goes
It's not.
up to 99.
Yeah, and even then, I bet it takes a while for it to crank out a 99 by 99 matrix. Now, a computer could handle that okay. A computer that's got more processing power and it can allocate memory, then you can do really big matrices. A calculator's going to struggle a little bit with that. Okay, so there's our calculator method. So what are these things good for? Okay, here's one example. There is, when we're trying to calculate areas of triangles, what's our formula for an area of a triangle? 1/2 base times height, good. There's another formula called Heron's formula that works also, and it's based on the side lengths of the triangle. But in either case, you've got to know some things about the triangle that may not be convenient. What if your triangle is situated on the XY plane, so it's situated in a two-dimensional space, so it's not convenient to calculate a base and a height or side lengths? You'd have to literally go in and use the distance formula and make all those calculations and potentially get some pretty ugly numbers to deal with. Now, we can all do that, but it's time-consuming, and you can see it's inconvenient. There's a way to do this with matrices using determinants. It's very simple. If I just know the coordinates of the vertices, I can calculate the area with this really simple determinant formula. Now, let me tell you what this means. It just means that now you gotta look how this thing's constructed. So if we call the vertices 1, 2, and 3 and give them the corresponding ordered pairs. So we'll call this one x1, y1, x2, y2, x3, y3. Understand, those are going to be numbers for us, right? Those are the numbers of the coordinates, the ordered pairs. If I put those into a 3 by 3 matrix like this, so we're going to put the first column is just going to be the x coordinates, second column is going to be the y coordinates, and the third column is just going to be 1. You're just going to literally, every time you'll just put in a third column that consists of only ones. Then if you calculate 1/2 times the determinant of that matrix, you're either going to get the area or the opposite of the area. So your answer is going to end up being maybe positive, maybe negative. If you just take the absolute value of that, so you always want a positive result, that gives you the area. Isn't that great? I mean, that saves you a lot of time. Yes, sir?
Why does it say negative
Plus or minus. Okay, and that's right. What it really probably should say is absolute value. The reason I think that they don't have it listed that way sometimes in formulas is because absolute value looks like a determinant when you're dealing with matrices. So all that plus or minus means is the area that this gives you is going to have either a positive or a negative sign. You always want it to be positive, obviously, because it's an area, and areas are always positive, right? So if you get a negative answer, what do? You just multiply by -1 and make it positive. See what I'm saying? Okay, so let's try one. Try this, see if you can set this up and get this to work on your calculators. So those are the coordinates of the vertices. See if you can calculate an area using that formula.
How do we, where do we go on that?
So I'll write the formula down for you. Okay, so the area equals the absolute value of the determinant of what? What's the matrix I'm going to take a determinant of? And everyone could come up with a different one. It doesn't matter which vertex you call point 1 and point 2 and point 3. You just have to be consistent. So what's one way I could construct that matrix that would work? What would the first row be? Okay, I could use this point. That's fine. Then I'd get what? 1, 2, 1, right? Because the third column's always just ones. What's the second row going to be? 6, 2, 1. Last row, 4, 0, 1. And those rows could be in any order, it doesn't matter, right? But they just have to be consistent, self-consistent. So, see what we get. So if I put those in the matrix, oh, so look what I did. That's the mistake that you don't want to do that. You have to quit before you go do something else because it was thinking that I was trying to put a determinant into that entry in the matrix.
Is that possible to put a determinant?
Yeah, you can. You can. Determinant's just a number, so
you
you
can
could.
get one ugly.
You can't, in fact, and there are situations where you do that, where you literally are putting a determinant in for one entry. I mean, you get some big matrix equations, formulas that look like that. Oh, and now here's something else I can do. Look at this. So I can save some time here. I built my matrix A, but I've already done that operation previously, right? So if I go back up with my new matrix A that I defined, if I go back up and I grab that operation and just repeat it, that's my answer.
Is it positive?
So it's going to be positive, though. Exactly. It's going to be positive. Yep. Say it again. Oh, and I forgot the 1/2, didn't I? Yeah, there's supposed to be a 1/2 out front. You're right. So what we need to do, there's supposed to be a 1/2 out there.
Okay, so how do we make it?
So then I could just say, right, so I could just multiply that, or I could even do this. I could say 0.5 times that, right, gives me -5, but we know to make it positive.
Okay,
Yeah, so it's
we
fine.
have to do it G first, then
Divided by 5. Divided by 2 or times 0.5. Okay, makes sense? Yes, ma'am. Yeah, I want to show you one other thing with this, yeah. And then, would you rather, I mean, I don't care. I can either do the inverse stuff today, and we can take partial lab days today and Friday, or take a whole lab day on Friday, or we can split it up. It's up to you. I don't care. Whichever you prefer.
Whole lab day on Friday.
Whole lab day on Friday? Is that better? So we'll vote. I gotta show you one more thing with this, though. There's one more little application you can do of this that's pretty slick. So in addition to this formula that I just showed you, telling you the area of a triangle, now this kind of makes sense. This is pretty cool if you think about how this works. Okay, what would happen, in what case would the area of that triangle be equal to 0? What could happen with those 3 vertices that would force that area to be 0? There's only one way that could happen. What would that be? Now think geometrically. What's the only way that triangle could sort of devolve into, it ended up being a non-triangle, but in what case would that area get pushed down to 0? What would have to happen to the vertices? No? Well, they could be any place on the plane, but yeah. They'd have to be collinear, right? Do you see that? If I took this point and I dragged, for example, this point down onto that line, wouldn't that drag the area to 0? Right? Okay, so that gives us a kind of a nice test for collinearity, doesn't it? If I take 3 points in a plane, if I know the coordinates of 3 points, and I find the area of the, I don't even need the 1/2 there anymore, right? If I just take the determinant associated with those 3 points, and I get a 0 answer, what's that telling me? That those 3 ordered pairs represent collinear points. See what I'm saying? So you can really quickly test for collinearity, which is kind of nice to do. That's a quick test. Otherwise, it's a little bit hard to know if they're collinear. I mean, we can do it. We can do it other ways, but that's a quick way. Okay? All right, so moving on. You guys, I'm not going to give you another example of that. You can do that fine. That's no big deal. Okay. Identity and inverse matrices. Okay, so let's talk about this a little bit, because this is a big concept, really important concept. And remember at the beginning of this unit on matrices, I talked to you a little bit. I told you that one of the things I want you to do is to think about how matrices are sort of equivalent to real numbers. So think about all the stuff you do with real numbers, and then there's these weird matrices, and they share some properties, right? So let's just forget about matrices for a moment and just think back to just all the stuff we've done with real numbers, which has been everything we've ever done in math. What does an inverse mean? What does the word mean to you? It could mean opposite. Yeah, it could mean opposite. In fact, the inverse for multiplication is an opposite. Yeah, I mean for addition is subtraction, right? So it's kind of the opposite process or the undoing process, the reverse process. So we can think of the inverse of addition is subtraction, right? What's the inverse of multiplication? Division. Yeah, good. Division. That's how we undo multiplication, right? And when we talk in a little bit, we've mentioned this a little bit already, but when we go back and talk more about this later on, we'll spend a lot more time with this in future years. When we talk about inverse functions, remember what the test of an inverse function is. I want to quickly share this with you or remind you of this because this comes up a lot in math. If I have two functions, if f of x and g of x, they don't even have to be functions, they could just be relations. If f of x and g of x are inverses, then this is what has to happen. If I nest the two, if I take a composition of the two functions, f of g of x has to equal x, and g of f of x has to also equal x. That must be true if these are going to be inverses. So what did that really just do there? If I take f of the function g of x, they literally undid each other and just left me with that x, right? If I take g of f of x, what did that do? Well, they also undid each other and just left me with the x. What's an example of that? A cube root and a cube function. So we could say, for example, if f of x equals x cubed and g of x equals the cube root of x, then what's f of g of x? Well, wouldn't that just be, instead of an x being cubed, I'm cubing the cube root of x. And what does that do? A cube root cubed undoes the cube root, doesn't it? Right? And I just get back x. You see what I'm getting at? And then if I flip that around and do g of f of x, it would just be the cube root of, instead of the cube root of x, it's the cube root of x cubed, which is also x. Right? And that's not really what we're talking about right now, but it's really important to me that you're clear with what I mean by inverse. Inverse is sort of the reverse process, right? Questions on that? Is that ringing a bell? Okay. All right, so now how does that apply here? Well, you're right. The inverse of multiplication is division. What does identity mean? Okay, this is the other part that comes up. What does identity mean? I mean, in real life, what's your identity is kind of who you are, right? That's complex. You're all complex people with lots of things that contribute to your overall identity. I mean, I couldn't describe it very simply. But in math, it's much easier. The identity of a number is just its value. Okay, so what's the multiplicative identity? What could we multiply by and preserve identity? I mean, that's pretty obvious. And we've already talked about this. 1. Is that, what's the additive identity? What do we add to anything and keep? 0. Yeah. Okay. Okay, so if we know that 1 is the multiplicative identity, then here's the part that I really want you to tie together in your brains. If that's the multiplicative identity, then the multiplicative inverse is what we can multiply by to get that answer, right? So in other words, 5 times what is equal to 1? 1/5. Now, multiplying by 1/5 is equivalent to doing what? Dividing by 5. Okay, good. So you already told me that the inverse for multiplication is division. You're correct. But more precisely, what it really is multiplying by an inverse. Okay? The inverse operation is indeed dividing. But for matrices, and the reason this is an important distinction is for matrices, you can't divide. You can't divide matrices. Instead, you have to do this. You have to multiply by the equivalent of a reciprocal. You have to multiply by an inverse. So the inverse of a number is simply its reciprocal for multiplication. Question, Kim?
How come you can't divide?
It's a very good question. I don't even really have a good, easy answer for you. It's just not defined. It's just not something that's defined for matrices. You can sort of think about it that way, but what you're really doing is multiplying by an inverse. Okay? So any matrix multiplied by its inverse, then, is going to give you back what we call the identity matrix. Just like a number multiplied by its inverse gives you back 1, the identity number, right? So we know for multiplication, we would just say 3 times 1/3 equals that special number 1. Now for matrices, it's going to give you back the matrix equivalent of 1. Okay? What is the matrix equivalent of 1? Okay? We call it, instead of a number 1, we give it a capital I, which indicates identity. That's the matrix equivalent of 1. Why don't we just say 1? Well, because it doesn't look like 1. It looks like this. For a 2 by 2 matrix, it looks like this is the identity matrix. It's got a descending diagonal of 1s, and everything else is a 0. So for a 3 by 3, it looks like that. You get the pattern. For a 10 by 10, it would just still have that one descending diagonal that contains all 1s, and everything else would be a 0. Every other entry would be a 0. So the identity matrix is always a square matrix, so it multiplies by anything with that number of columns or rows. And it has this look to it. On your calculator, this is kind of cool. I'll show you something you can even do on your calculator. You can pull up, if you go to the math menu, check this out. So second matrix math, identity, right there, 5. If I pull up identity, it wants me to put something in the parentheses. What does it need, you suppose? If I want to pull up an identity matrix, what does it need to know from me?
A matrix.
Yeah, but what? I can't just hit enter. Just saying identity matrix isn't enough because there isn't just one. You have to specify something about it. What do you think? Yeah, what the dimensions are. And being as it's always a square matrix, one number is really enough, isn't it? Because that one number is telling us both the number of rows and columns. So if I put identity 5, for example, That's what it does. Okay, it builds me a 5 by 5 matrix that has that identity look to it. Descending diagonal, all ones, everything else is 0. Okay, make sense? So matrices are weird. I told you that before. They're a little strange. This is how we say 1, but we have to pick the right one that matches our matrix that we're using. Okay, we have to pick the right size identity matrix. Okay, so just like the number 5 times 1 equals 5, some matrix A times the identity matrix is A. And the identity matrix times A is also A. Now that's important because normally matrix multiplication is not commutative. So I can't just say in general that matrix A times matrix B equals matrix B times matrix A, right? And we know why that is. Because what if, I want to just reiterate this because I don't want you to lose sight of this. If matrix A has dimensions 3 by 2 and matrix B has dimensions 2 by 4, do they multiply?
Yeah, no.
They do, don't they? Right? They multiply to give me a 3 by 4 matrix. But if I commute those, matrix B times matrix A, well, that would be a 2 by 4 times a 3 by 2. Do they multiply? No, they don't, right? The interior dimensions don't match up. Those numbers have to be the same to multiply. And they don't. So you can see, once again, that matrix multiplication is not commutative. You can't switch them around, except you can in this case. With an identity matrix, you can. Okay? Okay, so that's true. We could prove it on our calculators. I'm not even going to mess with that. That's also true. That's supposed to be a bracket there. I can multiply from either side by an identity matrix and it works. Okay, so how could we determine that? Now here's where you got to do a little thinking. How, if I give you two matrices like this, how could I determine if they are inverses? What was true of inverses? If two matrices are inverses, what's true? What do you think? Anybody got an idea? Yes?
They're square, they tend to keep up your matrices.
Okay, the matrices, okay, you're actually onto something there, but what did we say has to happen if two things are inverses? Like if I multiply, we said 5, what's the inverse of 5 for multiplication? 1/5, right? It's reciprocal. And if I multiply those together, what do I get? 1. If I multiply a number by its inverse, I always get back the identity number 1. Now, what's the matrix equivalent of that? If I multiply two matrices that are inverses, like 5 and 1/5, or what do I have to get back? I got to get back the matrix version of 1, which is what we just looked at. That's the identity matrix, right? So I could check. I could see if I just multiplied matrix A times matrix B and I got the identity matrix, then they're inverses, right? That's one way to check. Okay, with our calculators, turns out there's maybe even an easier way, and I want to show you how to calculate an inverse, and it's painfully simple. If I want to calculate the inverse of A, how do you think I do that on a calculator? What do you think? Pretty similar to how you calculated the determinant. What do you think? Yes, ma'am. Okay, yeah, good. I'm gonna put the matrix into the calculator as matrix A, and let's just use one we've already got in there. How about? So I already have a 3 by 3 matrix in there for A. Pretend we want to find the inverse of that. All I have to do is call up matrix A and hit the inverse button. It's that simple. If I hit enter, that's the inverse of that 3 by 3 matrix right there. Okay, I can prove it because if I multiply this one A inverse times matrix A, watch what happens. Well, what's that trying to say? Now, this is a little goofy sometimes. Your calculator will do this. It's saying 1, 1, 1. What is 1.3 e negative 13?
Zero.
That's 0, isn't it? That's a negative 1.3 preceded by 13 zeros. So it's 0.00000000000013 negative. Now, why does your calculator do that? Because they just aren't perfect. They just make these little numerical calculations. Should it be that or should it be 0? Well, 0. It should be 0. But your calculator sometimes will be off by a tiny little bit. And it's a little bit annoying that the calculators aren't quite smart enough to know that that's supposed to be a 0. But if you were to, for example, put your calculator into a mode where it was only keeping, like 6 decimal places, it would write that as 0. So just know, you guys have to know when you see that on a calculator, you're thinking, oh, whoops, it's really trying to say 0. Because that'll happen sometimes. Okay, make sense? Okay, that actually, I think, gets us far enough to where I can give you the inverse assignment, and we're good to go. Yeah, you don't need to see this stuff. I'll show you how to calculate an inverse by hand for a 2x2, but that's all we'll do. We'll do that next time.